Welcome to Chapter 1, Section 8, Logarithmic Functions. Important fact, logarithms are the inverse of exponential functions. If you can understand what that says, you will actually have conquered logarithmic functions. Don't worry if you don't understand why they're inverses, just accept it. So they allow us to undo exponential functions and solve for the exponent. They are commonly used to express quantities that vary widely in size. What that means is if I have f of x equals the square root of x, okay, and I want to know what its inverse function is, the inverse of it, or f inverse of x, if I go through all the steps, would equal x squared. And if I compose f with the inverse function, what I'm going to get is f of f inverse of x, which is equal to f of, well, f inverse is x squared, which is equal to, if I plug in x squared in for f of x, I get the square root of x squared, which is equal to x. So what is that? Why did I tell you all that? Notice they're inverses of each other. So that's how we cancel functions. The square root is a function and squared is a function. If I want them to go away, I take the inverse, and that's exactly what happens. Okay? So if logarithmic functions and exponential functions are inverses of each other, if I have f of x is equal to the log base b of x, and that's the inverse of the exponential function, we can write it in this notation as b to the x. These are inverses. Okay. Now, this means that if b to the a equals c, then the log is equal to a. And some people have learned this, and I'll show this part to you because it's a very nice way to remember, or just to kind of look at a function and be able to see what it means. So if I have log base b of c equals a, if I take an arrow from b to a and back to c, sometimes I've heard people refer to this as the around the world rule. You can kind of see we're going around. This is equivalent to b to the a equals c. So I go in this order: b to the power of a is equal, because I have this equal, to c. Okay? So whatever way you like, I don't care. I don't actually care which way you do things, as long as you do them properly. This right here. So just like I said before, they're inverse functions. Remember here, at the top here, when I combined or took the composition of the inverse function, I ended up with x. If I do it the other way, I'll also end up with x. What I mean is f inverse of x, f inverse of f, composition of x, is equal to f inverse of f of x. We replace f of x with square root of x. So I have f inverse of the square root of x, which is equal to, now I plug the square root of x in for x in the second equation. I have the square root of x squared, which again equals x. So it's very important to note, you don't necessarily need it for this class, but it is of note that when I do the composition of inverse functions, I always get x. Why is that important? Because it explains these two properties, right? If I were to say, if I were to say f of x is equal to b to the x and f inverse of x is equal to log base b of x, then if I do the composition of the two functions, I get x. If I do the composition of the two functions, it's the same as saying f of f inverse of x, which is the same as f of, well, we said f inverse is log base b of x. And then I'm going to plug that into my function, which is b to the power of log base b of x. And if they're inverses, these cancel. And I'm left with x. And the same is true in the opposite direction. So a visual of it could be log base b of b, cancel, and we get x. B to the log base b, cancel, and we get x. That is a very important property. We're going to be using it quite often to solve equations. So let's get on with it. For me, now for you, you might want to just memorize things. So if you want to memorize things, go ahead. First, I'm going to do it the way I would like to teach it to you, and then we'll do it a different way. So write these exponential equations as logarithmic equations. So what I can do is I can take the log of both sides. I don't have a base in there, do I? But if I want to use one of my inverse properties, then if I have a base equal to b right here, everything will cancel except the 3. What I mean by that is, let's make these both base 2. So now I have property 1 of the inverse properties, log base b, which is 2, of b, which is 2, to the third power. This equals 3. So 3 equals the log base 2 of 8. I've now turned my exponential into a log. And if we apply that around the world rule, I have 2 to the third power is equal to 8. Okay, so that's the way I like to do it. That's the way I'm going to teach you to do it. That way you won't make mistakes. If you would like, you're always welcome to just memorize it. So since I have a base of 5, I'm going to make the log base 5. Okay? And we can, if we do it to one side, we have to do it to both sides. These cancel, and I end up with 2 equals the log base 5 of 25. And again, 5 squared equals 25, just like we said. So we have 10 to the negative 4 equals 1 over 10,000. I'm going to take the log base 10 of both sides, because I know that if I take the log of a base, to the same argument, they cancel. So I'm going to do that to both sides. So that of 1 over 10,000. These will cancel, and I will get -4 equals log base 10 of 1 over 10,000. Now, when we have log base 10, if you notice on our little calculator here, I have log and ln. I have no place to put a base. Base 10 is called the common log. So log base 10 we don't need to put the base in. Just like we don't need to put 1x, it's assumed. This is called the common log. So we actually don't need our 10. So if I wanted to finish the problem above, I can just say -4 equals log of 1 over 10,000. And actually, let's prove it. Let's put it into our calculator. We have the log of 1 divided by 10,000. Notice it equals -4, just like we said. Okay. So that's basically how you can move it around. If you have logs on both sides, you can use this other function, the second one, and that gets rid of my log. I take the exponent of both sides. We'll see how that works. For this one, we want to solve 2 to the x is equal to 10. Well, it's very difficult to solve some. I don't know what to put in my calculator for this, right? I can't divide both sides by 2. I can't do anything. Except I can take my inverse function. This is an exponential. So the inverse is log. I'm going to take the log, and I'm going to use base 2 since I have a 2 here. Log base 2 of 10. According to my top formula, I can cancel this with this, and I end up with x equals log base 2 of 10. I cannot put that into the calculator. We need another formula called change of base formula, and we haven't learned it yet, so I'm not going to use it yet. Now we have, well, I already talked to you about common log. The common log is the logarithm with base 10, just like I said. The natural log is the log with base e, and that's what the ln function is. So if you see here, it's not in, it's ln. This is log base 10. This is log base e. Okay? So if I evaluate log of 1,000 using the definition of common log, this is the same as log base 10 of 10 to the 3rd power. And if I use that rule, these cancel, and that equals 3. Boom. And I can change all the values as long as it's base 10, then it's just the same as the log. If I want to put in here the log And we know that this is base 10 of 1,003. Okay? Easy. Evaluate log 500 using your calculator or computer. Well, we already kind of been figuring this out along the way. 5. This equals 2.699. Notice, I just want you to notice, logs are not linear because here at the top, the log of 1,000 was 3, and the log of 500 is not 1/2 of 3. So it has its own function. Be careful. Here we have, this is called the exponent property, often called the power rule. Okay? And basically what it does is it says, here, let me make this a lot bigger. We're taking the exponent on the thing inside parentheses, and we're literally bringing it to the front. That's all that's happening. I could explain why. I don't want to get too detailed with you because it doesn't matter. Bring it to the front. You can only do that if you have the function called logarithms or a log. You can't do that for anything else. X squared is not equal to 2x. The log of x squared is equal to 2 times the log of x. That's the only time you can use it. So whenever we want to solve exponential equations, we'll do them in this order. We're going to isolate the exponential expression when possible. That means take the b to the x, whatever that is, and just like if I wanted to solve for x, I get everything away from the x. Here, I'm getting everything away from b to the x. Then I take the log of both sides, and then I utilize the exponent property of logarithms to pull the variable out of the exponent, and then we'll use algebra to solve. Okay? Okay, here we go. So in the last section, we predicted the population in billions of India T years after 2008 by using this function, if you remember. If the population continues this trend, when will the population reach 2 billion? Okay, so now f of x is equal to 2 billion, which we said was 10 to the 9th. And actually, it started at 1.14 billion. So I'm going to actually rewrite this as 1.14 times 10 to the 9th, because it was in billions, times 1 plus 0.0134 to the t power. Okay, so I can start off probably the way they did by dividing both sides by 10 to the 9th power. And I end up with 2 is equal to 1.14 times 1. I can add this myself, 1.0134 to the t power. Now, it's very difficult to solve an equation with t as an exponent. Basically, the only way to do it is trial and error. But let's go down here. I'm going to take this piece here because I want to show you the steps. Notice what we're trying to do is isolate the exponential expression. So my exponential expression is right here. To do that, I'm going to divide both sides by 1.14. And now I have isolated my exponential function, haven't I? So check. take the log of both sides. And I can use either log or I can use ln. It does not make a difference. But I'm going to use the log of both sides since that's all we've really dealt with so far. And that's going to equal the log of 1.0134 to the t power. Now, I did that. Use the exponent property for logarithms to pull the variable out of the exponent. That's one way to do it, or we can use our power rule. So our power rule says that if we have log base b of a to the r power, we can move this r in the front, and then we just have log base b of a. That's what I'm going to do. So here's where I am. This is where I left off. I can say that the log of 2 divided by 1.14 is equal to, using the exponent rule or the power rule, t times the log of 1.0134. Okay? Done. Now it says use algebra to solve for the variable. All right. We're going through the steps. I'm going to delete this. We don't need it because we are now just going to use algebra. Okay, so again, I can just put this into a calculator, but let's see the algebra part first. I have the log of 2 divided by 1.14. And if I want to solve for t, I can divide both sides by the log of 1.0134, right? That's going to leave me with t. Now I can just put this into my calculator. So let's do it. We get the log of, so let me go back to main, 2 divided by 1.14 and parentheses. Why did it give me the extra parentheses? I don't know, but I don't need it. That's all I need. I'm going to take this whole thing and I'm going to divide it by the log of 1.0134 in parentheses. And now I know t is equal to 42.23. I can solve for t even when it says an exponent because I can take the inverse that cancels out the exponential function. Once I don't have an exponential function, I just have a log function. I can put it into my calculator and find out what t equals. Okay? Let's do one more. I'm starting with 5e to the minus 0.3t equals 2. Remember the steps. First thing I want to do is I want to get my exponential function by itself. So I want this by itself. That's my exponential function. To do that, what I need to do is divide both sides by 5. This will cancel, and I'll end up with e to the minus 0.3 t equals 2/5. Now I want to use my inverse function. My inverse of the exponential function where the base is e, the best way to do that is to take ln of e to the minus 0.3t equals ln of 2/5. Why am I picking ln? Because this is the same as log base e of e to the negative 0.3t. And remember, I can cancel these and I end up with just negative 0.3t equals the natural log of 2/5. And then to solve for t, I can divide both sides by negative 0.3. And this cancels. I end up with t equals. And let's clear this. I really just put this into my calculator. I have ln of 2 divided by 5, sorry. That's my numerator. I'm going to take this numerator and I'm going to divide it by negative 0.3. And my answer is t equals 3.05. Let's stop there. 3.05. That's how I solve for t. I don't really know what this equation represents. It doesn't matter. But if someone gives it to me, I can solve it for t. Okay? And then last but not least, let's talk a little bit about what the graph of a logarithm looks like, because again, it's important to understand. Notice what the shape is. Remember, just to help, if we remember, the exponential function always has a horizontal asymptote at y equals 0. It always goes through the point 0, 1. It always goes through the point when this is 1. So we have one point here, that's at 0, 1. And we have another point here, and that point is at b. So we have a point at 1, comma b. Okay? That's basically how the exponential function works, right? We've seen this before. Now, if we know that exponential and logarithmic functions are inverses, what that means is they reflect around this y equal x line, x comma y, then the inverse function is y comma x. They flip. So if I have a 0.01 on my exponential function, I'm going to have a 0.10 on my logarithmic function. If I have a 0.1b on my exponential function, I'm going to have a 0.b1 on my logarithmic function. Okay? X and Y flip. If I have an asymptote at y equals 0 for my exponential function, I have a vertical asymptote at x equals 0. Let me write for exponential. So this right here, we'll call this b to the x, and I will call this graph log base b of x. Notice they reflect around that yellow y equal x line, which is a mathematical truth about inverse functions. They reflect around y equal x. So we can see now that this is the shape of the log function, which is reflected here. Okay. Now, notice they're all going through the point 1, 0. Depending on my base is what makes the log function change how fast it increases. Okay? But its reverse of the exponential. Log base 2 has the biggest slope. Log base e, remember e is approximately 2.72. And the last one, b is 10. So we can tell how the shape is changing, and it depends on the base. But I wanted to show you, if it helps, if you remember the exponential function, which is purple, then the log just reflects and has the asymptote going the opposite. So my blue graph is my log graph. So when sketching a general logarithm, we have base b. It can be helpful to remember that the graph will pass through these 2 points, just like I said, because exponentials are 0, 1 and 1b, logs are 1, 0 and b, 1. So we already talked about the shapes of the graph above, and another important observation made was that the domain of the log is x is greater than 0, because we have that asymptote at x equals 0. It cannot actually touch that line, and it can't be negative. It only goes in the positive direction. That's very important to remember. So like the reciprocal and square root functions, the log has a restricted domain, which must be considered when finding the domain of the composition involving a log. Okay? So first here, let's find the domain of this function. It's not asking for anything else. All it says is, let's find the domain. Well, we know that we can only find the domain if the argument, this is called the argument, what's between the parentheses. So we said that if we have log of x, then x has to be greater than 0, not greater than or equal, greater than. So if I have the log of 5 minus 2x, and I want to know what the domain is, I have to say 5 minus 2x is got to be greater than 0. And now it's pretty easy to solve. I'm going to add 2x to both sides. I end up with 5 is greater than 2x. Divide both sides by 2. This cancels, and I have 5 halves is greater than x, or I can write it x is less than 5 halves, or I can write it as, if I put this on a number line, it's always easiest to do interval notation on a number line. So x is less than 5 halves. Let's call this 5 halves. And it's got an open circle there, and it goes that way. So I can see I'm going from negative infinity to 5 halves, and I have open bracket, open parentheses on both sides because it can't go to negative infinity is not a number, and it can't reach 5/2 or 2.5. And I think that will complete our logarithmic discussion. Thank you for watching. And next, we're actually going to begin calculus. Yay.